next module on clean arch. Welcome to our next module on clean architecture. I'm Matthew Renzi with Pluralsight, and in this module we'll learn about using commands and queries in our architecture. As an overview of this module, first we'll learn about commands and queries and how we should strive to keep them separated in our architecture. Next, we'll learn about 3 types of CQRS architectures. Then we'll discuss the pros and cons of CQRS practices. Finally, we'll take a look at the query side of our demo application. So let's get started. Bertrand Meyer taught us that there were 2 kinds of methods in object-oriented software. First, we have a command. A command does something, which means that it should modify the state of the system, but it should not return a value. Next, we have queries. A query answers a question, which means that it should not modify the state of the system, and it should return a value. Bertrand taught us that we should attempt to maintain command-query separation where possible. There are many reasons why this is a good idea. For example, to avoid nasty side effects that hide in methods that violate this principle. However, as Martin Fowler points out, this is not always possible. For example, if you have a stack and you want to pop the first item on the stack, the pop method removes the top item from the stack, which is a command, and returns that top item, which is a query. In addition, if you want to create a new database record, you create the database record, which is a command, but you may also need to return the newly created ID, which is a query. So there are clearly exceptions to this rule, but in general, we should strive to maintain command-query separation where possible. Command-query responsibility separation architectures, or CQRS architectures, expand this concept of command-query separation to the architectural level. In general, we're dividing the architecture into a command stack and a query stack starting at the application layer. This is done for various reasons. The primary reason is that queries should be optimized for reading data, whereas commands should be optimized for writing data. Commands execute behaviors in the domain model, mutate state, raise events, and write to the database. Queries use whatever means is most suitable to retrieve data from the database, project it into a format for presentation, and display it to the user. This change increases both the performance of the commands and queries, but equally important, it increases the clarity of the respective code. CQRS is domain-centric architecture done in a smart way. It knows when to talk to the domain via commands, and when to talk directly to the database via queries. There are 3 main types of CQRS which we'll take a look at next. The first type of CQRS we'll call single database CQRS for lack of an existing standardized name. This type of CQRS has a single database that is either a third normal form relational database or some type of NoSQL database. Commands execute behavior in the domain which modifies state, which is then saved to the database through the persistence layer, which is often an ORM that is an object relational mapper like NHibernate or Entity Framework. Queries are executed directly against the database using a thin data access layer, which is either an ORM using projections, linked to SQL, SQL scripts, or stored procedures. This single database CQRS is the simplest of the 3 types of CQRS architectures. The second type of CQRS architecture we'll call 2 database CQRS. This type of CQRS has both a read database and a write database. The command stack has its own database optimized for write operations. For example, a third normal form relational database or a NoSQL database. The query stack, however, uses a database optimized for read operations. For example, a first normal form relational database or some other denormalized read-optimized data store. The modifications to the write database are pushed into the read database either as a single coordinated transaction across both databases or using an eventual consistency pattern. That is, the 2 databases may be out of sync temporarily, but will always eventually become in sync, typically on the order of milliseconds. This type of CQRS is more complex than the first, but can afford orders of magnitude improvements in performance on the read side of the system. This makes quite a bit of sense because we generally spend orders of magnitude more time reading from a database than we do writing to it. The third type of CQRS system is typically referred to as event sourcing. The main difference here is that we do not store the current state of our entities in a normalized data store. Instead, we store just the state modifications to the entities over time, represented as events that have occurred to the entities. We store this historical record of all events in a persistence medium called an event store. When we need to use an entity in its current state, we replay the events that have occurred to that entity, and we end up with the current state of the entity. Then, once we've reconstructed the current state of the entity, we execute our domain logic and modify the state of the entities accordingly. This new event will then be stored in our event store so that it can be replayed as needed. Finally, we push the current state of our entity out to the read database, so our read queries will still be extremely fast. This is the most complex of the 3 types of CQRS, but it has some very powerful benefits in exchange for the additional costs. First, since the current state of each entity can only be derived by replaying the sequence of events that have occurred to that entity, the event store acts as a complete and guaranteed to be true audit trail for the entire system. This is highly valuable in heavily regulated industries where this type of auditability is necessary. Second, we can reconstruct the state of an entire entity at any point in time. This is useful for determining what the state of an entity was at any previous point in time in the system, and this is also very useful for debugging. Third, we can replay events to observe what happened in the system. This is very useful for diagnostics and debugging. In addition, this is also very useful for load testing and regression testing in a test environment using existing production events that have occurred in the system. Fourth, we can project the current state of our entities into more than one type of read-optimized data store. For example, we can simultaneously populate and then query fast text indexing services like Lucene, graph databases, OLAP cubes, in-memory databases, and more. This means that each query can request data from the data store optimized for querying and presenting the corresponding data. Finally, we can rebuild our production database just by playing the events. All we need to do to get the current state of our system is replay all of the events that have occurred in the past, and we end up with the current state of the system. These are some very powerful features if your architecture needs them. However, it can also be a significant additional expense if you don't actually need any of these features. In addition, despite the fact that most people new to event sourcing assume that the right side of the system will be slow, in reality, these systems are actually much faster than you would imagine. There are also several types of optimizations that can be added, like generating periodic snapshots, if the performance of the right side of the system becomes an issue. So why would we want to use a CQRS architecture? First, if you're implementing domain-centric design, implementing CQRS is more efficient from a coding perspective. Commands are coded to use the rich domain models to modify state, and queries are coded directly against the database to read data. Second, by using CQRS, we're optimizing the performance of both the query side and the command side for their respective purposes. Depending upon which type of CQRS we implement, this can mean orders of magnitude improvements in performance. Third, by using event sourcing, we gain all of the benefits we discussed previously and a few more that were not discussed. As systems become more complex or require high degrees of auditability, these features can become highly valuable to both the business and to the developers. So why would we not want to use CQRS? First, there's an intentional inconsistency in the design of the command stack versus the query stack. Inconsistency in general makes software more complex and difficult to reason about. However, we gain consistency within each stack as a trade-off. Second, with two-database CQRS, having both a read and write database is more complex and potentially introduces an eventual consistency model to your databases. Third, event sourcing entails higher costs to create and maintain the event sourcing features. If you'll not be deriving sufficient business value from these additional features, event sourcing might not pay for itself in the long run. So now, let's take a look at the query side of our demo application. Once again, I'm trying to keep things as simple as possible to teach you just the basic concepts without overwhelming you with the unnecessary complexities. As a result, I'm just going to show you an implementation of single database CQRS. That is, the first type of CQRS architecture that we looked at, which uses just a single database for both the read and the write side of the application. However, at the end of this course, I'll point you in the right direction to learn how to implement the more advanced CQRS architecture concepts. Let's start again with the sales controller class. As you may recall from the last demo, we injected two queries into the constructor of the controller via dependency injection. Then we used the first of these two queries in the index method to return a list of sales transactions, and we used the second query in the details method to return the details for a single sales transaction. Now let's take a look at the iGetSalesList query interface in the application project. This interface contains a single method called execute that takes no arguments and returns a list of sales list item models. The sales list item model class is a simple data transfer object that is a DTO in the application project that holds the data necessary to display a list of sales to the user. It only contains the data for a list of sales, however, it is not concerned with how this data will be presented to the user. That's the responsibility of the presentation layer. This data transfer object contains the following fields: sales ID, the sales transaction date, customer name, employee name, product name, the unit price of the product, the quantity of products sold, and the total price of the sales transaction. The getSalesList query class implements the iGetSalesList query interface. Once again, we're using dependency injection to substitute this getSalesList query class in place of the iGetSalesList query interface at runtime. So the sales controller will be delegating the call to the execute method on the interface to the execute method in this class. At the top of this class, we have a single private read-only field which contains a reference to the iDatabase service interface. We inject this interface into the constructor of the class at runtime using constructor injection in our IOC framework. The execute method for this class will query the database and return a list of sales list item models. We're going to be using link to entities with projections and fluent syntax to both simplify and optimize the query. So let's break this down so that we can understand each of the concepts I just mentioned. First, LINQ, spelled L-I-N-Q, stands for Language Integrated Query. It's a language feature in the .NET framework that allows you to write query expressions in the .NET languages like C#. Link to entities is a feature of Entity Framework that allows you to use link queries against entities in Entity Framework. Entity Framework then generates the appropriate SQL query to produce the data necessary to hydrate the entities. Fluent syntax is one of the two styles of link queries, the other being query expressions. It uses a concept known as method chaining to pass data from a child method into its parent method and so on up the links of the chain. Thus, we can chain together a series of methods to compose a complete link query. A projection is a subset of data with a different shape than the actual data stored in the database. For example, rather than pulling back all of the customer fields, employee fields, and product fields, which Entity Framework would do by default to create this list, instead, we just want the customer name, employee name, and the product name. Let's read through this query and see exactly what it's doing. First, we're accessing the sales repository of the database service interface. Next, we project data into our sales list item model using a link select method. In the class initializer of the sales list item model class, we set the following properties. We set the ID property of each sale list item model to the ID of our corresponding sales entity, date to the date of the sales transaction, customer name to the name property of the customer entity, employee name to the name of the employee, product name to the name of the product, and we also set unit price, quantity, and total price to the corresponding values of the sales entity. Finally, we call toList on the results of our sales query so that we're returning a list instead of an IEnumerable. This is beneficial for a few reasons, for example, to avoid multiple iterations over an IEnumerable collection, and to provide list semantics rather than enumerable collection semantics to the presentation layer. Writing our link query with a projection in this way is significantly different in terms of the SQL query that Entity Framework will generate, compared to if we used Entity Framework or any other ORM with either eager loading or lazy loading of related entities. In fact, to demonstrate how a projection simplifies the SQL query executed against the database, let's compare the three different types of queries. That is, an eagerly loaded query, a lazy loaded query, and finally, our projected query used in the demo application. The first query was generated by Entity Framework using a lazy load of all of the related entities in order to hydrate the entities necessary to produce the sales list. As we can see, this generates 10 queries, that is, one query for the sales data, and one query for each of the 3 customers, employees, and products related to the sales. In addition, when all 10 of these queries have been executed, these queries have essentially loaded the entire database, that is, all rows and all 4 tables, rather than only the data necessary to generate the sales list. This would produce very slow query response times and put excessive load on the database if the ORM was used this way. The second query was generated using an eager load of all the related entities. That is, it loaded the related entities on demand rather than one at a time like our previous query. As we can see, this reduced the number of queries down from 10 to a single query. However, this query is still loading the entire database, that is, all fields from all 4 tables when it is executed. While there are only 2 database fields in each of the related entities, that is, customers, employees, and products, if each of these entities had dozens of fields and dozens of rows, they would all need to be loaded in order to produce the sales list that we're trying to create. Finally, here's the query that was produced by the link to entities projection we created. As we can see, there's only a single query that is generated by our ORM. In addition, this query returns only the fields necessary to produce the list of sales transactions to display on the user interface. This is significantly more performant in terms of query time and significantly more efficient in terms of database load than our 2 previous examples. While this is a very simple example in this demo application, you can see how this simple change of separating commands and queries in our architecture and using the data access method most appropriate for the query side of the system can produce dramatically different results for your query performance and database load. The getSalesDetail query works pretty much the same as the getSalesList query we just saw. Once again, we use constructor injection to inject our database service dependency. In the execute method, we take in the unique identifier for the sale that we want to return details for. Then, we use link to entities with Fluent syntax to filter and project the entity into a model to return to the presentation layer. First, we access the sales repository of the database service. We select all rows where the ID of the sales record matches the specified sale ID. We project just the required fields into the properties of the sale detail model. Then we select a single element from this list since it should not be possible to have duplicate sales IDs in our database, and we return that single sale detail model to the presentation layer. While we used link to entities with Microsoft Entity Framework for the queries in this demo, we could have just as easily have used projections with NHibernate, link to SQL, embedded SQL queries, stored procedures, or many other data access methods. The key concept is that you should strive to separate your commands and queries and use a style of coding that works best for the respective command and query stacks in your system. Commands should read like high-level instructions working with entities in the domain model to modify state and save changes, while queries should bypass the domain model and query the database directly by whatever means is most appropriate to display the necessary data to the users. Implementing the other two kinds of CQRS, that is, to database CQRS and event sourcing, incorporates these same principles but does so in more advanced and powerful ways. In this module, first we learned about commands and queries and how we should strive to keep them separated in our architecture. Next, we learned about 3 types of CQRS architectures. Then, we discussed the pros and cons of CQRS practices. Finally, we took a look at the query side of our demo application. In the next module, we'll learn how to use functional cohesion to organize our classes, folders, and namespaces.